Janelle, do me a favor. Can you move to that table, to that chair over there, so that I don't have to turn so much back and forth? Thank you. Thank you. Thank you. Okay. You're which one in a very big rush? Okay. 7, you? Yeah, that's what I needed you to do. I needed you to tell me exactly which ones you want me to go through. So for Garen, 7, is it? Okay. Oh hell no, this is hard. Why is it so hard? Wow, this kind of question is so hard. Is released from X. I think very few people also know how to do this lah. To be honest, this is an A-level question.
I saw like one of the really smart guys, like his solution was like almost an entire page.
No. It's actually quite straightforward, but it's an A-level thing because it emphasizes on this equation, S equals to UT plus half AT squared. Okay, right? So it's a bit unfair. You also have to do this. You also have to use this equation, right? This Suvet equation. Do you? But do you have this equation? You have, right? I technically also can use the graph, you know, Karen. Technically also can use the graph on it. Let me show you the equation method first, lah. Actually, she's quite true also, right? She can also use the graph as well, but I'll show you how to do it. Okay. So the trick to doing this question, using that equation, right? The trick to using that one is always use the reference point from the start. Because at the start, right, at x, right, what is u? 0. So if you use that, right, then it becomes a little bit easier. So I have two distances that I need to consider, starting from x. I first distance is x to y, and the other distance is x to z. How do I find h? Correct, right? So x to z minus x to y, right? So h of xy. Okay, so far? Can Now s of xy. Let's work on this one first, right? What's the distance traveled from x to y? 0 plus half a t1 squared. You try to process that first. This distance, but remind you again, this is a A-level type of question. This is a little bit harder than normal. Like you say again, that guy go and do the working throughout the entire page, right? Technically, you don't need to, but I suspect it's because he didn't realize that you are supposed to use the original reference point, right? Reference point at x. So if you start at x, u is always 0. That's why ut is 0, right? And half at squared, right? But a is actually g, right? Isn't a gravitational field strength? Gravitational acceleration. So I'm just going to write g here. So sxy is half gt1 squared. Okay? How about s of xz? Since I start from x, right, what's the initial speed? 0 plus half gt2 squared. Because it says that it passes y at t1 and z at t2. So y at t1, z at t2. Fair or not? Okay. The trick is this minus this is the answer. Acceleration is g lah. So half gt2 squared minus half gt1 squared equals to h. Then you make g the subject. Yeah. So if you realize that, hey shit, actually it's just like that only. But it's not easy. It's not easy because the trick of this question is to use the starting point x as the reference point for both of them, so that the equations are very simple. The equation is 0 here and 0 here. So the very smart one, what he did was, he went to find the velocity at y, then he go and use the y at the u here like this. Then it becomes very complicated. I'm not even going to go and touch that. I'm just going to tell, if he comes looking for help, I'm going to just tell him that his method doesn't work. You have to use this method. You know what I mean? So I'm not going to even entertain that sort of like convoluted method, because it's just not worth explaining, not worth the time explaining that. Okay? So graph method, let's try. How about the graph method? Let's see. So the graph method will be VT. Okay? Then it will be this one. Let's see whether or not it will work. So let's say this one is T2 and this one is T1. H is the area under here. This is H. Okay? That's H. And basically you're supposed to find the acceleration, which is the gradient over there. So you have to find the gradient over here. Right? So I'll tell you that this is a little bit harder if you try to use the graphical method, right? Because this one here you have to find the GT1 and this one here is GT2. Yes. Do you understand why this is GT1 and why this is GT2? No, but I mean it's like on its own. Like you take G and then you times T1 and then you take G times T2. That's actually the speed at T1 and that's the speed at T2 because it's accelerating with G, right? So V equals to U plus AT, V equals to GT. Right, you see? V equals to U plus AT, V equals to 0 plus GT, V equals to GT. That's why the speed at T1 is GT1, the speed at T2 is GT2. Then you have to come out with the equation. How would you come out with the equation? Right, the area here is H, right? Big triangle minus small triangle gives you H. And you will end up with the exact same equation here. Yeah. Right, so be it the equation method or the graphical method, you can use both. You can use either. But you end up having to write down the same equation. This question not easy. Definitely not easy. Like this kind of so the thing is this, you need to strategize. So sometimes questions like this, right, you need to figure out that okay, this question is to be sacrificed on. Right? Just let go and then go and spend time on other things. Okay? So one by one, now your turn. Also 7. Okay, another one. What's this? So this is efficiency. Motor connected to power source that inputs 500 watts. So that's your input power. Diagram shows you the output power of the motor over 10 seconds. This is the whole 10 seconds. Then they ask you what's the efficiency of the... Ooh, this is not easy also. This is also another A-level type of questions. All right. I mean, obviously, right? So therefore, the difficult questions is definitely like the ones that stumps you, right? Okay, good. All right. So it's not easy because, okay, what's efficiency? Let's go with efficiency first. What's understanding of efficiency? Useful output over total input. Good. So that means your concepts are intact, right? But you just don't know what to do with it here, right? Look at this. Oh, do you want me to print out this one for you? Okay. So what we have here is the y-axis is useful power output, but the problem is the power output is not constant. And it changes with random amounts of time. It's like 200 watts here and then suddenly 300 watts there. Right? It's like all over the place, right? Okay, so the way to do this is to find the area under the graph. To find the area under the graph, okay? What's the area under the graph represent? So you can't take an average of 200, 300. You cannot say it's 250. Because the amount of time it spends at the 200 and the amount of time it spends being 300 is disproportionate. And then you have a period of time where it's changing as well. So it's very annoying. So what we do is we find the area under the graph. So what's the area under a power time graph? Energy, good. So this is the output energy. So instead of finding useful output power over total input power, you can find useful output energy over total input energy. Right? That will give you the exact same efficiency. So Based on that, can you find the area under this graph here? It's gonna be a bit nasty, because you got one rectangle, one trapezium, and another rectangle again. But if you can do that fast, can y'all do this quick math? 200 times 2, this is what? This 400, right? 400, then this one is 200, 300, 500, 500, 250, 250 times 3, 750. Right, and this one here is 5, 10, 5, 5, 300, 1005. Yeah, right. So what's the total output energy then? 400, 750, 1005, 400 plus 750 plus 1005, right? Then yeah, that I mean that's just 2650, right? 2650, 2650 joules. Okay, 2650 joules. Do you understand this? Yeah. Okay. Good. 2650 joules. And then what? 500 times 10 seconds. So the total input is 5000 joules, but the useful output is only 2650. So 2650 divided by 5000, right? You get 50 something percent. Look at your answers. Your answers are very close to each other. So 2650 divided by 5000, right? I get 53%. C is your answer. You got that? Yeah, yeah. That's not easy, but I mean you can understand it very quickly, right?
Are we supposed to know that the area under graph is not that?
No, I mean I think even my own practices and even your own school practices also you would have never seen this, right? So this is an like on the spot application question.
Like, how are we supposed to
How are you supposed to know? As in like you have to, I mean if you've done enough practices, maybe by chance you encounter a question like this before. To be honest, I haven't encountered this like for many years. I haven't seen a power time graph for a long time. Yeah. Just by experience lah. No choice lah. It's by experience. It's definitely by experience. I'm just yeah. Come next one. MCQ. You. Question 10. Right. What's the acceleration of box P when the cable breaks? What's the maximum? Oh what? Oh first is constant speed. Oh first is constant speed and then the cable breaks out. No reason. Okay. Can. Okay. So the question is this, Garen. Right, this is the application, but this you should be able to done it. The key phrase, right, that you should have paid attention to is constant speed. I didn't see you highlight it on your question paper. Right? Constant speed. So what's the deal with constant speed? Means what? Zero acceleration means what? No resultant force. No resultant force. Fnet is 0, right? So Fnet on the entire system is 0. So the pulling force must be how much in order for the entire system to have 0 resultant force. They did say that frictional force on each one is 3.2. So this one 3.2, this one 3.2, so therefore your pulling force is, so this one 3.2 newtons, this one 3.2 newtons, so the pulling force must be 6.4 newtons, yeah. See, then you look at the system, no resultant force, constant speed, right? But then somehow the cable breaks suddenly, right? Due to some random reason, the cable breaks suddenly, and then they ask you, so what's the acceleration of box P? Yeah. So P will be here, right? 6.4 newtons versus 3.2 newtons. Cable has broken, no more backwards force. So there's only these two forces. What's the resultant force acting on P? Fnet on P.
wait,
Yeah, ask. Yes. Yeah, it's 3.2. It's just 6.4 minus 3.2. 6.4 minus 3.2, right? Because the pulling force is this way, the reflection is pointing that way, right? So it ends up being 3.2 again, right? But 3.2 is the net force on P now. P's mass is 3.2 divided by 5, right? So Fnet equals MA, right? So A is equals to Fnet over M, right? So 3.2 over 5, which is how much? 0.64 meters per second squared. Okay, so B is your answer. So does box P accelerate? What will happen to box Q when the cable breaks? Don't I give you extra question? What will happen to box Q? It would decelerate. Why would it decelerate? There's no more pulling force, but there is still friction. Right, so it decelerate. What's the deceleration of box Q? Same, but same but different. P is getting faster. Q will get slower, but of the same magnitude. Okay, good. Next question, you. Irreverent. Here, this one. Okay. Okay. This thing here is called neutral, stable, unstable equilibrium. Right? Something that that you don't know whether you got learn or not. You did. Okay. What's unstable? Okay, I use ruler lah. I use my ruler is back. I use a ruler as an example. Oh, where's my ruler? Okay, ruler. Okay, where's the center of gravity of this ruler? Where? Somewhere in the middle here, right? Okay, good. Okay, if I pivot my ruler this way, right? This is the pivot. The center of gravity is above. Okay, if I tip it, the ruler topples. So what kind of equilibrium is this? This is unstable equilibrium. Why? Because a slight push will cause it to fall. Okay? Now, but what if I start from this position? Start from this position. This is my pivot. My center of gravity is below the pivot. If I were to give it a slight push, what will happen? It will go back to the original position. This is a stable equilibrium. So if you hold it like that, tip it, falls down, that's unstable. If you hold it like this, tip it, goes back, this is stable. There are three types: stable, unstable, and the last one is neutral. So how do you do neutral? You pivot at the CG. Because if you pivot at the CG, at the center of gravity, you tip it, it doesn't topple, it doesn't return back to its original position, right? Because the weight of the ruler is being pivoted here, so it doesn't create any moment, so it can't rotate any further, right? So remember this, neutral equilibrium will remain at its new position. You get the joke? Neutral equilibrium stays in its new position, all right? Okay, so there you go. So if you want to hold it so that it falls to a new position, you see, these people are being annoying. Falls there, they use the word fall, you know. Does it look like it was falling? So it's not falling, it stays. They should have used the word stay. But obviously the teacher is trying to be funny. The teacher is trying to see, I want to see whether the students can understand or not. Right? So sometimes I can detect whether the teacher is being annoying. Right? So the answer here is, it will be in position Y only, right? Be held so that it falls to a new position. Oh, falls to a new position, not stays. Goodness, I got it wrong. I read it wrongly. Oh gosh. Falls, that means it falls. It literally falls. They want it to fall. So X or Z. So the answer is C. So if you pivot it at Y, it will stay at the new position. Oh, yeah lah, unstable lah. So basically, they're asking for unstable lah, right? They're asking for unstable. So, gosh, so annoying. Okay. Did they even go through this question in class? Okay, so fall to a new position. Basically, whatever I showed you in my ruler just now, right? So I pivot it at Z, I tip it, it falls to a new position. Okay, can So if they had said stay in the new position, then the answer is pivot Y. Pivot at Y, okay? But if you pivot it at X like this, pivot at X like this, when you tip it, it returns back to its original position. It doesn't fall to its new position. Next one, come, you. 11. What's the horizontal component of a 50 Newton force? Aiyo. Okay. No, like this is correct. Yeah. So, but the thing is that the force is acting 60 degrees to the horizontal, right? It's 50 newtons, right? They want the extra in your class, in your school, and then you let me know, then I can go through with you. But actually, I did this, Yeah, I did this, Right? Yeah, no, that's why I thought I went through this before. You're supposed to do your trigo. It's a triangle. It's a triangle. Where's the triangle? I mean, you drew this first, but I don't see your triangle. So this is 50 and this is 60 degrees. Right? Yeah. So what's the horizontal component? What's the vertical component? Horizontal is 50 cosine 60 degrees. Vertical is 50 sine 60 degrees. Yeah, so it's 50 cosine 60. But do you know why it's written like that? Like, what's that about? Yeah, it's trigo. It's just trigo only. 50 cosine 60. Can? It's trigo. You write this, you draw this in your diagram. This is the more important learning point. Oh gosh. Okay, you. No, no more. Now paper 2. Okay, now paper 2. Wow, paper 1, that's it. You? Okay, paper 2 now. Very quickly, paper 2. So, which questions you want me to explain to you guys? Oh, your scan is damn jialat.
The document, when they scanned it for us, it was already done.
Oh my god, okay. Hey, what's up with all this scan here, scan there one? I was like, don't understand one, no. No, so, yeah, so the two sides, the teachers are talking to each other. The departments are both talking to each other. Yeah, no, Amber told me they're not going to return it to you at all. Sorry. Yeah, but no, at first I thought you don't even have your paper. Then only after when you came in, then you tell me that your paper is scanned at the bottom. Then I hounded her for it. I was like, hey, hello, the paper is at the bottom of the document. Then I think then she realized, oh yeah, goodness. Hey, sharp a bit, can sharp a bit, okay? All right, just. Okay, come, your paper 2. Which one do you want me to go through for you? 21A. The distance traveled from A to C. Hey, area under the graph lah. That one you don't know, I also don't know, brother. Sister, I mean. Then you have to look at the values carefully. This is 5, right? Ma'am, this is 5. This is a 10. Yeah? And then this one is a what? What's that? Is it 16.5? Is it 17? What's that? A to C, right? Oh, that's a 16. Right? 15, 16, right? 16 here. So that's a 16. And this one here is a 14. Yo. Half times 5 times 10 plus half times 5 plus 16 times 4. Area of trapezium. Not a physics issue, math issue, right? Okay, good, clear. You. Tell me. Examples not accepted. Brother, I need to understand what you're writing. I cannot see what you're writing. Oh, no. Okay, so no. So here's the thing. What you're asking is it just a definition? Right? Yes, the answer is just a definition. So systematic error, random error is just based on the definition. They ask you, state one difference, right? So you just go with definition. So systematic error is an error where the magnitude is constant. Right? For all readings. And the magnitude and direction of the error is constant for all readings. An example is 0 error. That's a systematic error. Okay? Random error is an error that has no constant magnitude and no constant direction. That means it can happen more than or less than, a little bit more than or very much less than, right? That's a random error. Okay, so you have to go with definition. So the thing is this, can you find this definition in your school's notes? Yeah, you can. Okay, you can, right? Good. Round robin, your turn. 23A. You know which ones you're gonna ask next already? Okay, hang on, let me just finish this. 23. Why? What's going on here? Then that's not an issue. Okay, you ask you. Oh, this 22. Sorry. 23A. This one here. Using Newton's third law, describe action-reaction pair associated with the expulsion of exhaust gases. Okay, so you have to be very strict with third law. I believe, no, you haven't done this with me yet. You only joined last week only, okay? Third law, tell me what's third law? Okay, drop me a message. Ask me for concepts on third law. Now, so that I remember to send you. Okay? Right? Because I can spend the next 7 minutes explaining to you what Newton's third law is about. But I got a feeling you didn't catch it. Or maybe you have a very vague idea of what it is. Right? To me, I think it's a vague idea. You might think that it's a very clear idea, but I mean, the way I hear you describe it, I think it's a very vague idea. So I want you to be very, very clear on what an action-reaction pair is. Okay? I'll send you the clip. It's just that I can save time now. I send you the clip. I don't have to go through it now. You know what I mean? Okay. Then after that, then you see for yourself why the answer is like this. Right? I give you a very short clue on it. Newton's third law, right, basically says this. If there's a force by A on B, to quote the Newton's third law, then you have to quote the force by B on A. Okay? So you read the question over here. Read this one here. The rocket exerts a force on the exhaust gas. Right? There's a engine burning, right? The fuel, and therefore the rocket's fuel container is here. The gases are expelled downwards. Okay? So the rocket exerts a downwards force on the exhaust gas. By Newton's third law, the exhaust gas exerts a equal and upwards force on the rocket. On A by B on A, you get your marks here. Can? But I still want you to go through the details of the lesson first, right? So, I mean, nothing can be covered in a short period of time, so you sometimes have to go through the whole thing. Come, your turn. This one? Why? Okay. So calculate the distance traveled. No, lower. In reality, air resistance is present. Calculate now draw the speed time graph during the first 12 seconds. Assume other forces acting remain unchanged. Okay, so let me ask you this. Glider is getting faster. Right, the glider is getting faster. Okay, so your intention was correct. You wanted to show that the speed increases at a decreasing rate. That's why you draw the graph like this. Okay. The problem is air resistance will act on the glider, so therefore it will make the acceleration less. You draw a graph like this, right? You're showing that acceleration is greater than the original one. No, look at the steepness of the graph. Look at how steep your graph is. This part here. See this? Your gradient is this high when the original gradient was only like that. Okay? So how should you draw the graph then? Your graph should look like this. Look. You need to show that the initial gradient at the start is similar, and then as it accelerates, its acceleration will never be higher or even equal to the original glider acceleration without air resistance. So if there's air resistance, it should look like this. Oh, slower as well. Okay, so it goes like this, right?
Yeah.
Something like that. Sure. Okay, can ah? Right. So therefore, that I mean, yeah lah. That's a bit wasted there. What's the next one for you? So all these okay. This one okay. Let me just double check. No marking is okay. So your one is 27. So okay. Okay, can. Okay. Have you fixed all this ready? This idea of unstable equilibrium and all that? Yeah? Okay, Right. So okay, then the next one is, well, let me see first. Have you fixed this ready? Okay. Oh, they're very nitpicky with the phrasing, because you cannot write same pressure. You have to say the no difference in pressure, right? Or the same change. 27 D part 2, is it? On figure 27, draw the position of the wave for t equals to 0.1 seconds. Okay. What is the period of this wave? Sorry. Oh, you don't know what's the period. You only know the frequency. So give me the period first. Frequency of 5, period is what? 1/5. Okay? 1/5 means what? 0.2 seconds. Okay? So the time taken for one full wave is 0.2 seconds. The question is asking you to draw the wave 0.1 seconds later. That means they want you to draw the wave half a wave later. So this is half a wave, right? Half a wavelength. So back on this diagram here, sorry, which one's the original one? The original one is this one, right? This one's the original one, huh? Okay. So basically you need to shift it by half. So your equilibrium line is in the middle here, right? And therefore, half a wave later, it will look like this. You basically have to just draw like the opposite of the, like you flip the wave around like that. Yeah, you just flip it over like this. But it actually means that it has moved like this. Right, let me show you very quickly, in case you can't visualize it. Right, and then I will do. Okay. So what happens is that you have a wave that's going to move half a wave later, and therefore when you draw the picture of the original wave and the new wave, right, they're just kind of like they look like the opposite each other, but it's actually they shifted already. Okay, Garen, next one, you. 32 32D. What's 32D? This one?
The air resistance acting on the glider was equal to the weight of the glider, hence the author below the force allowing the glider to maintain a constant speed.
This question is not oh shit, this question is not fair. Okay. Where's the weight acting? This mg, right? It's not a fair question. So the idea here is that the glider has no more pulling force, nothing, right? There's only weight, right? And air resistance. So the question is, how does the air resistance act on it? right? Since the glider is now angled downwards like this, right? So the idea is that here is that the glider has two air resistances. One is acting backwards and one is acting upwards. Like that. No. It's acting along this way like that, and one is acting perpendicularly to it, something like that. Yeah. It's not a very fair question at all. This okay. If I want to keep it very simple and not overcomplicate it for you, I think you will only really understand this when you're in J1, right? Because now there's really no need to. So we just focus on one thing. Constant speed means what? No acceleration resultant force is, which means that the forces acting on the glider are balanced, right? Like the balance, right? Okay, so what are the forces acting on the glider? And so air resistance balances the weight. Like you just give a stupid statement down there like that, you get your mark already. I guess right? But you the air resistance what? I can't see what's that. Huh? Okay, so we don't say equal, we say balance. Okay? Equal means what? Equal means same magnitude and same direction. The air resistance not pointing in the same direction as the weight. It's pointing opposite, right? So you have to change it to balance. Okay, so just understand, just learn how to use the word balance. Your turn, Janelle. That's it. Then, do I want to look at it? Hey, you got ultrasound what? Oh, but the time interval you have to halve it, all right? Yeah. Yeah, you have to halve it. Yeah. So good lah. I mean, okay, be very careful. The lines at the back here are supposed to dotted. Dotted lines is for what? If you drew dotted, it will penalize. Hey, that's it for you. You sure? Yeah. Let me be a judge of that first. Where? I see. Oh, you it looks like you're getting marks. Mm-hmm. Oh, like this one here. But your MCQ your MCQ is the one that caused you to lose a lot of marks. What was the breakdown of your scores again? 23 out of 30. Are you sure? Yeah, it's damn hard to look at this thing. So you see, right, the weird thing about your papers, guys, the way I see it is this. I see some questions, right, are very dead simple, you know. Like some questions like, pop, like what's going on? Then yet the questions you ask me, right, those are like, what the hell, why are they giving you A-level questions there? So they mix in a bit, you know what I mean? So you got to learn the trick, especially for both your schools. They will throw some A-level questions down to make you lose composure. It's your job to learn how to ignore those and then move on and do the ones that you can do. And do those properly. Okay? So phrasing is a very big thing in your mark scheme. Right? So phrasing. And rightfully so also, because once you get into JC A-levels, right? Phrasing for any science, right, is super important now. You use the wrong phrases, they're gonna mark you down. Unfortunately, it feels a lot like PSLE again. You remember in PSLE, you have to use the stupid CER concept, right? All that, right? You have to do that, right? It's the same thing again. You have to use proper phrasing. Okay? But to be honest, at the A levels, it's not so stringent. It's not like so nitpicky like that, right? I think it's a school thing. Can your questions didn't have a lot of phrasing. Her questions, a lot of questions are phrasing on. Yeah. Your one is a lot of calculation questions, but then your careless mistakes all make you lose marks everywhere here and there. But actually, it's MCQ, leh.